this. Okay, so it was actually great to hear about from Grady about the interplanetary internet and the progress in using DTN. Like many of the speakers here, in thinking about 2070, it caused me to sort of think back, try to understand sort of, what do networks look like when we think about these long time scales? Grady actually mentioned telegraphy and some of the work in, kind of Civil War era. He might be interested. There was actually, before the electronic telegraphy I have here, the French actually had a complete optical telegraphy system that was active in the 1700s. So long history of store and forward networks being used, and they're really pretty long-lived. So, telegraphy finally kind of, closed up shop in 1980, went a long time. What's interesting here are a couple things. One is you see sort of these midlife kickers where new technologies were added in that really extended the utility and the lifetime of the network. Also, in this case, the store and forward network was augmented with improved storage. Initially, the storage in this network was people writing messages on paper at the switch points, and then people started using punch tape, which was a big improvement. So then, whoops, sorry about this, going too fast. Circuit switch telephony took hold, and look at the timeline of how long this sucker lasted. I'm dating it as starting really from, storage your step-by-step switch. That switch, there were lots of innovations between 1890 and 1965 that improved the switch, improved the scaling, added multiplexing, lots of things. For 65, I'm focusing on a big one that matters to most of us, which was the addition of a stored program computer controlling the setting of the switches. So now the circuit switching was controlled by software. And then with SS7, an interesting innovation where they moved from in-band signaling to out-of-band signaling, which is kind of interesting because that's actually the same thing we're doing with the internet. The original internet was sort of in-band signaling, and SDN is a form of out-of-band signaling. Finally, in the sort of 70s and 80s, there was an innovation of actually kind of turning this into effectively a digital system that was kind of switching packets, except the packets were only 1 byte large. So they were starting to use storage in the network, and except it was only sort of 1 byte per line card and 1 byte per time slot that was being switched. So then we see packet switching overlapped, right? It got started. Each of these networks, as somebody indicated before, gets kind of built out of the pieces of the prior technology. We started with, the ARPANET. What was really going on here, though, interesting enough, is, again, use of more storage in the network, more memory in the network. My God, we had, buffers that were the size of whole packets, and we had multiple of them per node and per line card. This was, in its day, a huge amount of memory. We evolved from ARPANET to the internet. From internet, we've been adding in SDN, as I said, in-band, out-of-band switching. But the key innovation here really was the use of memory within the network that allowed packet switching. That allowed us statistical multiplexing. It allowed us rate adaptation. So the two ends didn't have to actually operate at the same speed. It allowed us burst absorption. All sorts of great capabilities flowed from it. And as somebody indicated earlier, I think it was Mustafa, also effectively this was the key groundwork for the OneNet, because now you could actually run many, many different types of applications instead of being built for a single application. And again, it was kind of this use of memory and buffering that provided the ability to adapt. Now, meanwhile, while we were kind of exploiting storage, the cellular access people were exploiting information theory and kept figuring out how to get more bits per hertz jammed down the channels. And I think this has been a sort of exciting series of developments. So they were really using computing information theory to further the cause. And as somebody pointed out earlier, great innovation within the hyperscalers. So we moved, into piling all the servers into data centers. Those got bigger and bigger. People started realizing they could build custom networks. If you're inside your own data center, you could start having a custom network. In fact, you could interconnect your data center with custom networks. And that really kind of got us to an important question that's come up earlier today, which is We think of the internet as a global network. Somebody sort of mentioned that one net carries most of the traffic, but I don't actually think that's true anymore. In fact, kind of the situation we're in is we've got these access networks that kind of cover the first millisecond or so. Folks like the hyperscalers have, extended their networks to get very close to everybody. They've got pops, sort of pretty much within a millisecond of everybody. And to some degree, what we think of as the internet protocol and BGP and all of that is almost just a connector, a plug that connects these. It's kind of not really running on a global basis anymore. And meanwhile, as other people have also pointed out, we've had other parts of the world start going in other directions. Fan Mingqing is, recognized sometimes as the father of the Great Firewall of China. We've had sort of other countries sort of figure out that maybe they wanted to run under a different value system. I'm going to leave the politics of that aside and say that one of the things I find that's going on right now is a proposal coming out of China for what they're calling new IP. And so really we have kind of folks saying, you know what, we're going to develop a whole new generation. We're going to kind of replace that internet style packet switching with something new. If you look at the research agenda, actually it's very much the research agenda many parts of the internet community have followed. So I don't think we argue with it per se, but the thing I want to point out is there was a time when we, the packet switching folks, were, the disruptors, and we were disrupting circuit switching. These folks are going to go off and build their thing, and I think we need to counter that and rise to that challenge and figure out how we're going to build the next thing for the next 50 years. One of the things we need to do in doing that is kind of repartition concerns. Right now, each of these communities, whether it's the hyperscalers, the 3GPP crowd, or our, internet community, we all think we're doing the full end-to-end architecture for everything. And in practice, the 3GPP folks, I think somebody mentioned this earlier, Henning, what we really want from those folks is just do that first, kilometer, that first millisecond of traffic really, really well. Don't worry so much about the end-to-end network. And so, maybe we have to figure out how we all kind of work together to bring about a future. And one of the things that I want to point out is NSF has started this RISE program, RINGS program recently. And I think what's really exciting about it isn't just the technical agenda that includes some of these issues, but actually that they've brought together all the players. And that really has the opportunity for people to figure out how we might coexist differently in the future. Okay, so let's say that, rings-like stuff gets us through the, the next 10 to 20 years, then what? We could take a look. People have talked about some of these, what I think of as evergreen constraints. So some of these design requirements, privacy, security, all of these listed here are not going to go away. I see these as still being valid in 50 years. An interesting question is, what about physics? How constrained are we going to be there? Does innovation slow down now that Moore's law has come to an end? Well, some folks have posited that, no, we're just going to start using custom accelerators, et cetera. I think that I'm really excited about that. I love it, but I think it's only going to get us about another 10 to 20 years, and then it's going to run out of steam. Quantum computing, when I was at DARPA when we were making some of the first investments there, and at the time we figured late 20s is, when it would likely come into play, and I think sort of 1930 is still late 20s, 2030 is still a good timetable. However, what we see now, I think, is that it's going to have some really interesting applications, but they're limited. They're going to be things like simulations, optimization, solving big problems, interesting problems, much better than we could, but they're not going to be the panacea. So what are we going to do? What's going to power our innovation going forward? I'm going to argue that we can break free of physics, that algorithms can actually be the rocket fuel that could sustain a pace of innovation going forward. That, essentially one of the things people haven't realized is during the past 20, 30 years, algorithms have also been a huge source of, optimization and improvement and efficiency. Really, there's been tremendous innovation in that space. And perhaps by getting better and better at that, we can sort of essentially use that as a way to have the, effectively feel like we've been improving the compute as we go on from decade to decade. I think we can also throw those algorithms at getting more goodput out of our network. So effectively, even if we don't keep getting, sort of faster and faster optical speeds and, we don't necessarily get more classical bits per hertz. Maybe we can get more goodput bits per hertz. And I want to talk about that a bit in a few moments. So, okay, so what will that innovation be used for? What will the computer communication applications be? Hopefully not more CAD photos. I think machine learning will be really an important, continue to be an important application that's going to grow and grow for at least a few more decades, maybe for the full 50 years, but hopefully not DNNs. That's a whole other talk. So machine learning, but not DNNs. I do think that IoT, whether you call it IoT or machine to machine, or really we should think of it as machine to cloud, I think that's the thing that's really going to sop up our attention. And a particular flavor is the transition from interactive computing. That is the agenda that really was laid out in the 60s for the computing community. It's the agenda that's dominated for the kind of first 50 years. I think starting about 10 years ago, we really started to make progress on what I think of as proactive computing, systems that anticipate our needs and act on our behalf. And we really have this opportunity to bring, kind of prediction and faster than real-time simulation and fuse that with, our ability to pull data out of the physical world around us. So I think there's tremendous opportunities there. This is something that I think Jim sort of indicated as well, the opportunity to have enormous societal and economic impact. So raise our attention to the application and to societal scale applications. Okay, so what tools can we use? What are the tools I think that networking folks can use to really guide us and drive the change over these 50 years? One thing I've learned is it's sometimes good to look and say, what's getting to be in surplus? What is starting to get to be overbuilt? It may not be available to us. I really learned this, in the 2000 downturn. We had a problem that the cost of data was just too high, and it didn't really make sense. Data was being kind of priced to hold up the price of voice because that's where all the money was. And people were actually overbuilding their fiber networks. And when the 2000 downturn hit, that kind of suddenly, unleashed the demons and allowed us to really get data priced appropriately because there's recognition suddenly that there's a huge surplus of fiber capacity. I think there's going to be some huge surplus, not right away, but in a couple decades of access capacity. In the urban areas, somebody mentioned that the various Gs typically don't live up to what they promise. So 5G isn't really going to give its gigabits to every user, but 6G probably will, and that's probably going to be overkill. So that's going to give us some extra capacity to be used. In rural areas, these LEO satellites, in rural areas, the irony is there's plenty of hertz per person. So there's plenty of spectrum out there. We just have to figure out how to use it better. The other thing we're going to find is that we're going to have great access to low-cost sensors, low-cost, low-power, because today all those folks building cameras, cameras now are starting to exceed the limits of human vision. So they're going multispectral. They're going to be giving us a really cheap supply of high bandwidth sensors. So we have this future ability to cost effectively instrument the physical world, very high fidelity. Okay, so surplus we can use. I mentioned before the notion that the history of networking in some ways has been adding more and more memory into the network. So storage in the network, I think, can really power things. Now, I never heard Dave Cheriton say this, but it's the sort of thing he would have said, that it's the content stupid. And he would have said that when he was sort of launching his take on content routing in the internet. But there's been this history. Somebody again mentioned this before, and Scott's written a really nice paper on seeing the forest for the trees. I know there were other authors there, Scott, but I hear your voice when I read the paper. And Leisha gave us a sort of nice keynote on this not too long ago. But the real question I want to raise is so why hasn't this actually gone further? In Scott's paper, one of the things that they identify, and again, it did come out here earlier, is that there's sort of this long tail of content. And once you've had Akamai sort of take advantage of the head of the tail, maybe there's not that much benefit to be realized. Now, in looking at this, I think that maybe we've been a little too simplistic there. In that we've really just been thinking in terms of trying to optimize for that the whole benefit of content networking might be the caching in the network. I think there's a lot more that can be recognized. I want to think we could bring network coding to bear, but also if we look at BitTorrent, I think People focused on its peer-to-peer aspects and various things there. One of the things in there, the idea of a torrent file, the idea of having a recipe for what you wanted. If you think of that torrent file, it sort of gave you the metadata, and then you went and assembled all the parts of the content you wanted. I think that's quite powerful. We could go a lot further with that. So we've got, I think, the surplus, we've got storage. What else? Surprise! No, I actually really mean it. I mean surprise from an information theory perspective. The basic idea of information theory is that the value of a message depends on the degree to which the content of the message is surprising. So imagine what we could do if we really thought about surprise through the lens of the application. And we start thinking, very carefully about, so what's surprising? When we go to deliver content, how should we think about delivering old content? It doesn't really have very much surprise. Today people focus a lot on movies and all that stuff, but maybe only, sports and, stock prices or the, news are the only actual important information. I meant that from a classical point of view. I think there's lots of upstream information, all that stuff we learn from the physical world. We only need to deliver the surprising part of it. So there's incredible opportunities for us to improve the good put, but even more interestingly, to, I think, allow whole new applications by fusing the old information with the new, by kind of downloading, pre-computing lots of pre-simulated possibilities in the core of the network, in the cloud, downloading those models. That's what machine learning models really are. It's kind of the opportunistic computing of the past. And it captures all the old information and then combining that with the new and doing that, inference and fusion in the network. So I think there's lots of opportunity there. I think another thing that's been holding us back, and Scott actually has commented on this, and he identified the problem and has identified the solution, is our obsession with the narrow waist. We love these sort of layered models, but Alice and Bob, they only really care about getting the information from one place to another. They really couldn't care about our sort of, view of hourglasses, et cetera. So I think that it's a mindset thing. If we start thinking much more about application layer relaying, putting the services, it could be the service nodes, et cetera, but putting some application relaying in the network that is smart about the applications, and then over time figuring out how to move that down the hourglass and absorb in the important things. So, putting it all together, we want to kind of combine, I think, these three things over the next 50 years. I think the applications will be proactive computing. They give us, I think, some tremendous social and economic benefits that we can realize. We can enable it by really figuring out how to take advantage of surprise and storage and getting really good at application layer relay. I think there's also a question of where should we do this? And as some people indicated, near the edge. Now, I say near the edge because if we could just put this within 1 millisecond of the sensors, actuators, and people, that would be more than sufficient. That 1 millisecond is a big area. I mean, that's a big circle. That's a 300-kilometer circle. And if you think about it, people's, our human capabilities are about 13 milliseconds for vision, 80 milliseconds for responses. So we'd have a ton of slump if we could just put that application relay within a millisecond. So lots of opportunity there. Stay away from ultra reliable, low latency communication. And we really need, as we do that application layer relaying, to embrace distributed computing. There's really kind of a gap between networking people and distributed computing folks today. So in terms of teaching, I love the way Jim actually teaches computer networking because he starts from the application. My plea would be add some information theory, add some distributed computing in here so that that's what, how we'll teach people differently in the future. And there's, you had to have a little bit of animation. So finally, for those of you that are starting now and planning to retire between now and 2070, here's some really good advice that I got from Bob Taylor. Be kind to interns. Someday they may keep you around, if only as a mascot.